Welcome to the video for Chapter 17. Today is kind of the hinge pen of the entire course. If you think of everything in the book so far as leading up to Chapter 17, and then everything after today is going to build off of what we see today in Chapter 17. So it's a very important day. It's hard to overstate the importance of bringing everything together into one complete set. We're going to start out today by introducing the concept of continuity equation. We're going to use that to prove why there needs to be displacement current. We'll add displacement current into Amperes law, and that will complete the set of Maxwell's equations. Then we'll briefly see an application of Maxwell's equations. It's a relatively long chapter, but I think it's going to move pretty quickly. We only have a few examples, so I think that it should not take too long. Obviously today, the historical perspective is going to be James Clerk Maxwell. He was a Scottish scientist. He formulated the comprehensive mathematical model that unites electricity, magnetism, and light. And I want to really emphasize that until Maxwell, electricity, magnetism, and light were thought to be three different phenomena. And only after he united them together was it seen that they were all one thing. That's actually a really big deal. And just as today people are working on unified theories of bringing together the four fundamental forces, it used to be that there were a lot more than four. And so being able to unite some of them together has really made a big difference and has really created our field of electrical and computer engineering. He's often considered the third greatest physicist of all time, of course after Newton, who would always have to be considered the greatest, and then Einstein, who I think has also, as you know, done tremendous work. So let's get into the new material for today, continuity equation. The continuity equation is really just a mathematical statement of the conservation of mass. We understand that if a particle exists, absent any sort of nuclear reactions, the particle has existed for all time and will exist for all time. That means that if we look at a picture like in figure 17.1, we understand that if particles are going to leave a region, then it's necessarily going to reduce the amount of particles that are left within the region. In the same way that if I buy a pizza for $10, my bank account has $10 less than it used to. So I've specifically shown here three particles crossing the boundary of this region, and you could think of those particles as representing a current I. And as that current I is leaving the region, or once it has left the region, then there are three holes left where there used to be particles, and so the contents of the region have gone down by 3. And we can have a mathematical statement of that, which simply says that the current is equal to negative dq dt. And here we're using the particles to be electrical charges, so I am representing them as q and I. The negative sign here simply indicates that if there is a current that is leaving the region, then it will bring about a decrease, a negative change in the particles that are within that region. So I equals negative dq dt, we can represent I as the surface integral of j, and q of course is going to be the integral of rho sub v with respect to v. Again, we're going to bring the d by dt, or the partial with respect to t, inside the integral. And so we end up with this expression right here. Then we're going to use the divergence theorem. And the divergence theorem is kind of just a mathematical statement of something that we've been using up until this point. And that is to say that if you look at the surface integral of all the particles that are leaving a region, so that's what the left-hand side is really talking about. If I have a region, and if I know that there is a net amount of particles, maybe there's some going in, but in general there's a net amount of particles that are going out, well, that has to be caused by a divergence. And that divergence, of course, represents the source of the particles. And so that must mean that somewhere inside of this region, there must be some sort of a source of whatever it is that's leaving. There's no way that it could be leaving, let's say that, well, maybe this one is wrapping around and is completing that one, but there's no way that there could be a net amount of particles leaving unless there was also a source. In the same way that if you saw me buying pizza every day, you'll eventually have to make the assumption that I've got a job, because how else could I afford that pizza every day? So if we find that the surface integral of all of the particles leaving the region is equal to the volume integral of the source of particles within that region. And so this divergence theorem, if you look at it, it essentially converts a surface, an integral over a surface, into an integral over a volume. And that can be extremely helpful to us. And in particular, we're going to apply it to the left side of equation 17.2, where we're going to convert that from a surface integral into a volume integral. And so you can see then that what we've done is we have applied the divergence theorem to the left side. Let me back up again here and show this used to be a surface integral of j dot ds, which is the same thing as it is right here, and instead it's going to become a volume integral of the divergence of j. And so there's the divergence of j, and that's the volume integral over the divergence of j. Now interestingly, equation 17.4, both sides of that equation are volume integrals over the same volume. So they're both integrated over the same volume. And if two volume integrals over the same volume are equal, then that must mean that whatever is being integrated has to be equal. So we can drop the integration and we can just see that the divergence of j is equal to negative partial of rho sub v with respect to t. So we've just taken whatever was being integrated on the left and we've set it equal to whatever is being integrated on the right. Don't forget the negative sign. But most typically the continuity equation is shown with both terms on the left so that they're both positive. So the divergence of j plus the partial of rho sub v with respect to t is equal to 0. Now we really derived that equation from first principles. There was no observation, there was no sort of relying on Maxwell's equations. It was really just conservation of mass. And so we know that this equation is going to be true 100% of the time. If we find something that disagrees with this equation, then we're going to have some concerns about the thing that led to the disagreement, because we know that equation 17.6 is correct. Equation 17.6, the continuity equation for electric charges, also has a lot of applications, and let's consider one of them here. Assume that somehow we've injected free charges into the interior of a conductor. Well, we know from our previous discussions that if you have a conductor, so let's imagine that I've got a conducting solid sphere right here, that if there happen to be charges, they're all going to move to the surface, and they're going to move to the surface to get as far away from each other as possible. And that means that inside, so in the interior of the conductor, there are no charges. Q equals 0, and E, therefore, is equal to 0. There's no electric field, and there are no charges. So how can we if we know that Q has to be 0 and E has to be 0, well, what happens if we override that, and instead we put a whole bunch of charges right here in the middle? So we've kind of violated the rules. The question is, what happens? Well, obviously, you've crowded these charges close together. They don't want to be close together. They have a lot of mobility because they're in a conductor. So since they're in a conductor, that means that it's going to be easy for them to move however they want to. They're going to go as far away from each other as possible, as quickly as possible. So the question is, how quickly will they move? Because eventually those charges are going to move away from the middle, and they're going to sort of also build up on the outer surface. If they could get even further away from each other, they would, but they can't. So they're going to have to tolerate just being on the surface there. So let's start with the continuity equation. We know that the divergence of j plus the partial of rho sub v with respect to time is equal to 0. We also know from Ohm's law that j is equal to sigma, whoops, that's not a vector, is equal to sigma times E. So that's Ohm's law. And we're going to plug that back up into the continuity equation. So this becomes the divergence of sigma times E plus the partial of rho sub v with respect to time is equal to 0. And then we know by Gauss's law that the divergence of E is equal to rho sub v over epsilon. That's Gauss's law. So even though we don't have all of our Maxwell's equations together yet, some of them are complete, and we're using those in this example. So I'm going to, so I took this one and I substituted it into that, and now I'm going to take this one and I'm going to substitute it into this. I've pulled the sigma out in front of the divergence, so this becomes sigma times rho sub v over epsilon plus partial of rho sub v with respect to time is equal to 0. And if you look at this, this is actually now a differential equation of only one variable, rho sub v. Sigma is a constant, epsilon is a constant. Let me rewrite this into a form that may be somewhat easier to recognize. Partial of rho sub v with respect to t plus sigma over epsilon times rho sub v is equal to 0. So we see here that this is a differential equation that you probably know the form of. We know then that rho sub v is going to have an initial value, rho sub v 0, times e to the minus, and it's going to be sigma over epsilon times t. And we know that another way of representing this is that it is rho sub v0 e to the minus t over tau. So we can combine those together to see that tau is equal to epsilon over sigma. And epsilon is 8.854 times 10 to the minus 12th. And in this particular example, we know that it's copper, which has a conductivity of about 6 times 10 to the 7th Siemens per meter. So this is 6 times 10 to the 7th. So when we do this calculation, we end up with 1.47 times 10 to the minus 19th seconds, which on a human scale is 0. I mean, from our perspective, that is happening instantaneously. The blink of an eye would be 1,000,000 years compared to this. But we do have the mathematics and the physics to answer the question. So let's go back to this equation right here, and I'm going to come up here and I say rho sub v divided by rho sub v0 is equal to e to the minus, well actually, you know what, I'm going to grab this version of it, is equal to e to the minus t over tau. And I know the question says, how long will it take the charge to dissipate to 1% of its initial value? So essentially, how long will it take to almost completely dissipate? So I'm going to take the natural, and so therefore I know that this is equal to 0.1. Because if rho sub v at a given time divided by the initial value of rho sub v0 is equal to 10%, then that's equal to 0.1. So I now have a mathematical equation that I can solve. So I'll take the natural log of both sides of this equation right here, and I get negative t over tau equals the natural log of 0.1. And t then is negative tau natural log of 0.1, which is negative 1.47 times 10 to the negative 19th seconds multiplied by the natural log of 0.1, which is negative 2.30, and then that takes us to 3.4 times 10 to the negative 19th seconds. So how long does it take for the charges to dissipate inside of a solid piece of copper? Practically no time. 3.4 times 10 to the negative 19 seconds. And unless you're dealing with a system that has time constants that are that long or that short, you can essentially say that it will happen instantaneously. As soon as you inject charge into a conductor, it will dissipate almost entirely. So it's interesting. We've been able to derive the continuity equation, which we have a great deal of confidence in. We've been able to use the continuity equation then to figure out what happens inside of a conductor. We wouldn't have been able to solve this example without the continuity equation. But of course, today's main point is Maxwell's equations, and in particular, completing the remaining missing piece of Ampere's law. So you might say, well, then why did you bother with the continuity equation? Was this like was this just like a side road that we went down? No, it's going to be important. You just have to have faith. So recall that we saw Ampere's law, and in chapter 11, I gave you a point form of Ampere's law that relates the magnetic flux density B to the current density. But even at the time, I said to you, it's not complete. There's a missing piece to Ampere's law. And so we can't put it into the official Maxwell's equations yet because we have to add the missing piece. Well, we can observe two problems with Ampere's law. And I got to tell you that it took basically 30 years from about 1840 until about 1870 for people to discover these problems and then to come up with the solution to these problems. So yes, I'm going to do it in about 5 minutes, but I want you to know that physicists spent their entire career trying to figure this problem out. It is incredibly difficult, and that's the reason why you know Maxwell's name today, is because he's the person who ultimately figured it out. So let's consider what's the main problem. Well, what's one problem is disagreement with the continuity equation. So we know from equation 11.12, so we're going to take our incomplete version of Ampere's law, and we're going to take the divergence of both sides. We can move the mu sub 0 out in front on the right-hand side, but we end up with the divergence on both sides. But mathematicians have told us that the divergence of the curl of any vector field is always equal to 0. So again, I'm resorting to trusting that mathematicians are telling us something that's correct, and they are all about making sure that they are 100% correct in their analysis. So we can have faith that this is true, if we divide both sides of that equation then by mu sub 0, then we end up with the fact that the divergence of J is equal to 0. And that just comes directly from Ampere's law. The problem, though, is that that disagrees with the continuity equation. Remember that the continuity equation said the divergence of J plus the partial of rho sub v with respect to t is equal to 0. Well, if those are both true, then that must mean that this partial of rho sub v with respect to t is equal to 0 at all times in all places. And it most certainly is not. Charge density is moving around all the time. So if you have to pick which of these two equations is correct, well, it's not this one. So we know that that is not correct. The analysis that we did to lead to that point was valid, so therefore we know that this equation is not correct. So we know that the quote incomplete version of Ampere's law is not valid. So you knew that because I told you it was incomplete. But if you try to put yourself in 1840 and say, oh, here's something that's been discovered, and now you come up with this analysis and you say, wait a minute, there's a problem with that. And we need to investigate that problem further because we know that the continuity equation is correct. And if the continuity equation is correct, then equation 11.12 cannot be correct. Well, here's problem number 2. Magnetic field near or inside of a capacitor. We understand that if we attach a capacitor to an AC voltage source, the current is going to flow. It's going to flow throughout the wire, and every time that there's a current flowing throughout the wire, there's going to be a magnetic field circulating around that current. So I've tried to represent that here with the little arrows to represent the current flowing, and the magnetic fields as the red loops that are circulating around that wire. And so we understand that. Our theory is complete on that, and actually Ampere's law, even in its incomplete form, gets that right. So the question is, what happens inside between the plates of a capacitor? And I've tried to sort of exaggerate the width of the capacitor here so that you can get a picture of what's going on. We have only two options, and that is to say that everywhere else, that the magnetic field is going to be everywhere else around this wire, but inside the plates of the capacitor, it's equal to 0, that there is no magnetic field inside of the plates. Or we have another problem, and that is that we would think, okay, well, I think that there is in fact a magnetic field inside of the plates, but if so, where is it coming from? Because if I scroll back up, remember that this equation says the only possible source of a magnetic field is a current density. And we know that between the plates of this capacitor, there is no current. So since I is equal to 0, we also therefore know that J is equal to 0. And if J is equal to 0, then B must be equal to 0. Well, you can imagine then what is as theorists are trying to figure this out, what do? They go and they measure it. They set up a capacitor and they measure it. And they say, is there in fact a magnetic field in between the plates? Does the magnetic field cut off at one plate and then restart at the other plate? Or is it continuous? Do we see that it's circulating around the wire, but then it's also circulating here as well, so that we get a nice smooth transition? And the answer is, there are magnetic fields in between the plates as well. But if there are magnetic fields between the plates, where are they coming from? Because our theory to this point doesn't handle that. It doesn't provide a source for those magnetic fields. So this is where Maxwell found himself, and this is why it took him many, many years, decades, to figure out the answer to this question. And the answer is that there's a term missing from Ampere's law. So let's consider how can we prove that how can we come up with a theory for Ampere's law that will allow us to find that there is in fact magnetic fields inside the plates of the capacitor, when the only thing that exists between the plates of the capacitor is an electric field. And if there is a dielectric, then there's also this displacement field as well, D. But really, D and E are really two sides of the same coin. So we have to figure out how to make a modification to Ampere's law. We're going to go back to the continuity equation, which again, we have complete confidence in the continuity equation because it was done from first principles of conservation of mass. We're then going to dip way back to chapter 8. And in chapter 8, we saw the final form of Gauss's law, which allowed us to include the effect of dielectric materials. And we're going to combine those together. We're going to take this divergence of D, we're going to put it in up here. And so we end up with equation 17.9, which says the divergence of J plus the partial derivative with respect to T of the divergence of D has to be equal to 0. Okay, well, I'm not sure that has helped us yet, but now let's factor the divergence out of both of those two terms. So again, this is something that a mathematician might get a little bit hinky about, but as long as you meet certain assumptions, you can factor the divergence out of both of those. And this is what we get. This is what we end up with. You can see, of course, the divergence up here is the divergence of J, and if we bring this divergence outside of the derivative, then what remains is the partial of d with respect to t. And so I end up with two terms in these parentheses. And what that makes me think about is that this, which I'll call this the conduction current, and conduction current is just what we've been thinking of. I'll call it conduction current density. This is what we've been calling current density for the entire semester so far. But there is a second term here, and that is that the partial of d with respect to t. This seems to sort of be like a current. You know, it is filling the role of a current in this equation. It's parallel or similar to, or fills a role similar to a current. So can we treat it like a current? Can we pretend that it's a current? Well, that's what we're going to do. We're going to call it the displacement current. So the displacement current, J sub d, because it is derived from the displacement field d. So J sub d is going to be defined as the partial derivative of d with respect to t. And with that new terminology, we can now rewrite equation 17.10, replacing the partial of d with respect to t with a simple J sub d. And later on, we're going to give a subscript to this other current density as well. We're going to call it J sub c. But for right now, we're just going to leave it as J because it's what we've been calling J so far all semester. Now remember, inside of a conductor, there is no electric field, and therefore there is no displacement field. So J sub d is going to be equal to 0. So in other words, if d is constant, it's constant at 0, then the derivative is going to be 0, and so therefore J sub d is going to be equal to 0. So inside of a conductor, there is no displacement current. And if there is no electric field, there can be no displacement current. Conversely, inside an insulator, or in free space, which is an insulator, there is no charge density, and if there is no charge density, then the conduction current J is also equal to 0. So conduction current only exists in conductors, and displacement current only exists in insulators, including free space. So we kind of have two terms here which almost never overlap. Now you could make the case that maybe in a semiconductor there's a little bit of conduction current and there's a little bit of displacement current. But in general, for most of the things we're going to be looking at, you'll have one or the other, but typically not both. Now we're going to go back to our incomplete form of Ampere's law. So remember that we have some problems with this form of Ampere's law. What I'm going to do is I'm going to take this mu sub 0, I'm going to move it over into the denominator of the left-hand side. That's going to leave just J on the right-hand side. And then, of course, what are we going to do? We're going to add J sub d as well. So this term right here, that is J sub d. And so now we have two different types of current on the right-hand side. There's J sub c if you want, and then there's also J sub d. We've moved the mu sub 0 over onto the left-hand side, and that is now the official final form of Ampere's law. Now you might not buy my case that partial of d with respect to t behaves like a current, so therefore we can treat it like a current. Here's what I'll tell you is that this equation perfectly matches every experiment that has ever been done in electromagnetic fields. It perfectly describes the magnetic field that surrounds around a conductor. It perfectly describes the magnetic field that surrounds an insulator, such as inside of a capacitor. It doesn't matter whether or not we think of partial of d with respect to t as being like a current. It gives the correct result. And it also, if we think of it as a displacement current, it makes it easier for us to be able to have intuition about this equation. And we can think of it as two different currents, that when you get to the boundary of a capacitor, you know, over here we have J sub c, or just J as we're moving from left to right. In between, now you could think of it as being J sub d, and then when we get back over to here, we get J sub c again. So it actually allows us to think of it as sort of a continuity of the current density as well. It kind of actually obeys Kirchhoff's current law there, as the J sub c is flowing in, J sub d is flowing out, and then J sub d is flowing in, and J sub c is flowing out. If you don't like that picture, then you can ignore that picture. I kind of like that picture, and it kind of makes it easier for me to think about how the system works. But regardless, equation 17.13 is the law. It is specifically, it's Ampere's law, and so we need to be prepared to use Ampere's law to model the behavior of our systems. We're going to take the surface integral of both sides of Ampere's law and over the same surface. Then we're going to apply Stokes Theorem. You might remember Stokes Theorem from the previous chapter. That's the one where we have a region, and within that region there's all kinds of circulation going on. Think of this as like a hurricane, and as the circulation is going on, it's leading to a circulation around the outer perimeter. And so we see that all of those little tiny twists and turns add up to the circulation that's going around the outer perimeter. That's Stokes Theorem. We're going to apply Stokes Theorem to the left-hand side, which converts a surface integral into a line integral. And when we do that, then we can apply b equals mu sub 0 times h to the left-hand side, and that simply converts b over mu sub 0 into h. And now we have the final form of Ampere's law in its integral form. So we now have Ampere's law in point form, Ampere's law in integral form. Those are now added to the three equations that we already had. Remember, we had Gauss's law. We had the equation that says there are no magnetic monopoles, which I kind of like to call Gauss's law for magnetic fields, because it talks about the source of magnetic fields. There is none. And then we also had Faraday's law, which we actually just recently saw. And now we have Ampere's law. Those are the four. Let's demonstrate that the magnetic field surrounding the capacitor in figure 17.3 has the same magnitude as the magnetic field surrounding the conductor. So essentially what I'm trying to do here is I'm trying to prove that if you have a capacitor and if there is a magnetic field that is surrounding the wire here, so if this is B, I'll call it B sub C for conductor, that if I calculate the magnetic field inside the capacitor, and I'll call that B sub D, for displacement, that's going to be equal to the magnetic field around the capacitor. I mean, a part of our analysis of this was to appeal to the fact that that magnetic field should be constant or should be continuous in between the plates, and so let's prove that it is. Let's see how we can prove that it is based on the new version of Ampere's law. So first of all, let's consider B sub C around the conductor. And this is actually going to be by far the easier part of this problem because we've already done this before. We understand how this works. So I'm going to take the full form of Ampere's law, integral of b over mu sub 0 dot dl is equal to the surface integral of j plus the partial of d with respect to t, and that's integrated over a surface. Now, since we're around a conductor, we aren't going to have any displacement current. So since there's no displacement current, that term's going to go away. The left-hand side, this is going to be, and let's specify if I'm looking end on at the wire, and then I'm trying to figure out what is the magnetic field around it. So if this is B, then I'm going to say this is rho. So the distance out there is rho. So B over mu sub 0 times the circumference of that circle is 2 pi rho, is going to be equal to the integral of j dot ds, which is just going to be equal to I. So then B is equal to mu sub 0 I over 2 pi rho. And so that's the magnetic flux that is B sub C, which I should have just called B sub C here to be consistent. So B sub C is mu sub 0 I over 2 pi rho. We're going to need to do some work to figure out what B sub D is, but ultimately the punchline needs to be that it's equal to the same quantity. Now, we're given V of t here. V of t is equal to V sub 0 sine of omega t. And so if I wanted to figure out how much current is flowing, I could use that voltage to do so. So now let's look at inside. Oh, let me be consistent here. So this is going to be B sub D inside the capacitor. B sub D inside the capacitor. I'm still going to start with the same Ampere's law. The integral of B dot dl is equal to the surface integral of the surface integral of j plus the partial of d with respect to t dotted with ds. And now since we're in an insulator, there are no conductors here, then j is going to be equal to 0. And so we have, I forgot that's a b over mu sub 0. Sorry about that. So I have b divided by mu sub 0, again multiplied by 2 pi rho, is equal to the surface integral of the partial of d with respect to t times ds. Now we're going to put that equation on the shelf for just a minute. It's going on the back burner because we don't know what the partial of d with respect to t is yet. So let's take a step back and let's see, what is I sub C? I sub C is the current into the conductor. You know what, I'm just going to call it I because we called it I in the past. So this is going to be equal to C dV dt. C dV dt. And we were given up above, let me scroll up here, we know that V of t is equal to V0 sine of omega t. So this is C times d by dt of V0 sine omega t. And so therefore I is equal to C times V0. The sine is going to become a cosine, but the chain rule is going to pick up an extra omega. So cosine of omega t. Now, we're going to have a couple of other relationships, but we need to remember what that current is. Now, we know that D is equal to epsilon times E. And we know that E, in this case, is the voltage across the capacitor divided by the distance inside the capacitor. So therefore, I can write that D is equal to epsilon times V divided by D. Let me also just take a minute and observe that we also know that the variable for capacitance is epsilon times A divided by D. So we have an equation for D, and we have an equation for C. Well, let's come back up here to the top, and I'm going to take this equation for D, which is going to be a valuable equation. We're going to take that one, and we're going to say D equals epsilon, well, you know what, I'm going to pull the D out here, so it's epsilon divided by D times V, which is going to be epsilon divided by D times, and that's V0, and it was sine omega t. And then I'm going to have that the partial of D with respect to t is epsilon over D V0, and then the partial of D is going to mean the sine becomes a cosine, and again, chain rule picks up an extra omega, so this becomes omega cosine omega t. And then I can plug this back into the equation that we put on the shelf. But remember that this equation right here, we put that one on the shelf, and now I'm going to come up here and I'm going to say B equals, I'm going to move the mu sub 0 over 2 pi rho over to the right-hand side, mu sub 0 over 2 pi rho times the integral of the partial of D with respect to t integrated over the surface area. Okay, so B is equal to mu sub 0 over 2 pi rho times the integral of, and I'm going to take this quantity and I'm going to plug it right there. So epsilon over D times V sub 0 omega cosine of omega t, all of that is dotted with ds. But none of the things in the square brackets there depends on the surface area. So the surface area is just going to add an a term. When we integrate with respect to ds, we're just going to pick up an extra a. So we got a lot of constants here. Mu sub 0 over 2 pi rho times epsilon over d times v sub 0 times omega times the cosine of omega t, and then times a from that surface integral. Okay, it's time now for us to begin gathering some of those constants together. I'm going to gather the a, so I'm going to gather the a and the epsilon over d. A over epsilon, a times epsilon over d, that's what we know to be the capacitance. So this is going to be mu sub 0 over 2 pi rho times the capacitance times v sub 0 omega cosine of omega t. And then I know that, let's see, I know that the capacitance, okay, I know, hold on, sometimes it's hard to keep track of what all I know. I need to now factor out what is I. So I know that I is equal to C, so there's a C, and times V0, there's a V0, there's an omega, and there's a cosine t. So this term right here is I. So this is equal to mu sub 0 I over 2 pi rho, and that's our final answer. And sure enough, these two quantities are equal to each other. We had to do a lot of work to get there, But what we found is that the magnetic field surrounding the capacitor, surrounding the inside the capacitor, is the same as the magnetic field that surrounds the conductor. And that gives us really good confidence that the analysis that we've done so far is correct. Incidentally, you can also do a little bit of extra work here, and not only did we prove, therefore, that B sub C is equal to B sub D. By the way, I'm sorry, this should have been B sub D up here. Yep, and that should have been B sub D, and that should have been B sub D over there. Not only did we prove that B sub C equals B sub D, but from the work that we've done here, it's trivial to prove that I sub C is equal to I sub D as well. So you can do that work on your own, but I think that it's you're in a good position now to be able to trust that this theory, in fact, is giving us the correct result for these magnetic fields. Okay, let's now assemble Maxwell's equations. We have 4 of them. We have Faraday's law of induction. We introduced that, I believe, last chapter, and it was complete upon introduction. We have Ampere's law with displacement current. So this term right here, that was the missing piece. It's like Maxwell, all that Maxwell really did was add that term and then assemble these 4 equations, put a box around them. But that's why they're called Maxwell's equations. So sometimes this is also known as Ampere's law with Maxwell's addition, but I like to call it Ampere's law with displacement current. We also have Gauss's law, and then we also have the Gauss's law for magnetic fields. Notice how this one is talking about what is the divergence of electric field, and this one's talking about what is the divergence of magnetic field. So, you know, the right-hand side is just equal to 0, which means that there is no source of a magnetic field. There are no magnetic monopoles, but I love the symmetry here. Notice the symmetry between these 2 equations, and then actually notice that there is a lot of symmetry between these 2 equations as well. The left-hand sides of these 2 equations are essentially identical to each other, except E versus H. The right-hand side, the right-hand sides are complete and they are fully correct. But notice that if I just scratch out the J, look how much symmetry there is on the right-hand side as well. There's a partial with respect to T. There's a surface integral. It's B versus D. We're going to see that in free space, like in outer space or in a vacuum, J does go to 0, and this actually does become a pair of equations that can be combined together to yield perhaps the most important result in the entire course. But for right now, we're going to leave J the way it is, and Maxwell's equations don't need annotations or arrows, so I'm erasing all of that so that you can have the sort of pristine version of it, because this is what we've been doing so far. I mean, everything in this class has been building to this point, and now we have Maxwell's equations, and everything we're going to do after this point is going to build off of Maxwell's equations. So again, it's like the first half of the class has been deriving these or observing them and making observations to get the things in this box, and now we're going to start to apply them. We also have point form. Remember that both integral and point form are both completely valid. They can be applied in different ways. Often I find the integral form easier to apply, but I love the elegance of the point form. It's very compact. It talks about, for example, what is the divergence? What is the source of an electric field? It is charge densities. What is the source of a magnetic field? There is none. And then if you have a changing magnetic flux, density, that creates an electric field. The electric field creates a voltage. And then if you have either a conduction current or displacement current, that will create a magnetic field surrounding it. So I think that the point form is really a very compact and elegant way of representing them. Now I mentioned before, and I'll mention them again, that there are 3 assistant equations, helper equations, called the constitutive equations. We see that D equals epsilon times E, that's the effect of a dielectric material. B equals mu times H, that's the effect of ferromagnetic materials. And then J equals sigma times E, that's Ohm's law. So those 3 equations, along with whichever set of 4 equations you choose to use, gives you everything you need to know about calculating E and calculating H and calculating B and calculating D. There is one other equation that we should include in a complete theory here, and that is the Lorentz force equation. Because remember that really up above we're just talking about how to calculate D, E, B, and H. But this equation allows us to see what is the effect of D, E, B, and H. So those, I guess there's 2 sets of 4, and then a set of 3, and then 1. So that's 12 equations. Those 12 equations, 4 of which are redundant with the other 4. So it's really 8 equations. Everything that we're going to see after this is going to be built off of those equations. Let's see an example of that, because I've been making a big deal about how we can use Maxwell's equations to derive really interesting results, and next time we're going to see the most interesting result you can derive from Maxwell's equations. But let's just briefly talk about what happens with charge diffusion. Charge diffusion, we can talk about electric fields, we can talk about magnetic fields, but in general, let's consider what happens inside of a conductor, because next time we're going to talk about what happens in free space. So in free space, it's really interesting. But it's also pretty interesting inside of a conductor. So let's focus at what happens inside of a conductor, something like copper. Now we actually just used, remember we used the continuity equation to see what happens when we place charges inside of the middle of a conductor. Now let's talk about what happens with magnetic flux. So we're going to start with Ampere's law. Since the displacement current is 0, this reduces down to equation 17.17. Remember that there was a plus d, partial of d with respect to t. But because we're inside of a conductor, there are no electric fields, and therefore that plus partial d with respect to t goes to 0. We're going to substitute Ohm's law on the right-hand side. So again, we're using one of the constitutive equations to modify this. Taking the curl of both sides of that equation, you might say, why are you doing this? Because a physicist spent a decade figuring out, oh, I wonder what happens if I take the curl of both sides. And we're going to now introduce this in 2 minutes, whereas they spent a decade to study it. Substituting Faraday's law on the right-hand side, so we have the curl of E is equal to the negative partial of B with respect to T, and then converting H to B on the left-hand side, so H becomes B over mu. We end up with equation 17.20, but we've already seen, and we're going to repeat now, if you have the curl of a function, that's equal to the gradient of the divergence of that function minus the Laplacian of that function. And we also talked about if we, quote, choose the Coulomb gauge, then that's like setting the reference voltage equal to 0. That can be chosen such that this first term goes to 0. And so if that first term goes to 0, then I'm just left with minus the Laplacian of b over mu equals minus the sigma times partial of b with respect to t. Obviously, the negative signs can cancel, and we're left with equation 17.22. Now, I want you to remember that this Laplacian operator really comes down to second derivatives with respect to space. There's an x component, a y component, and a z component. But we end up with essentially what is a differential equation that has second spatial derivative on the left and first time derivative on the right. Now we're going to rearrange this so that the mu sub 0 moves over to the right-hand side. Not much of a change there. And now let us consider the interface between a conductor and free space. So we have the blue region here as a conductor, we'll say copper, and then free space, we're going to apply a voltage, and I've tried to represent that here. We're applying, not a voltage, a magnetic field right at the surface of this conductor. So that magnetic field is being applied right at the surface here, and we're going to call it B sub x of z, because it's moving back and forth in the x direction. So it's moving back and forth in the x direction like this, but its strength is going to weaken as it goes into the material. So what we're going to find is that it's going to really decay and it's going to approach 0. Why is it decaying? Why is it approaching 0? Well, the magnetic field is causing electrons to circulate inside the conductor. Remember, a conductor is like nothing other than a sea of electrons, free charges that can respond to anything. And they're all responding to the Lorentz force that's created by this magnetic flux. And so as a result, as they're spinning, what does Lenz's law say? That the induced magnetic flux is going to oppose the applied magnetic flux. And so what we're going to find then is that it's going to oppose, which is going to weaken that, and then over a relatively short distance in most cases, it's going to approach 0. The question is, how quickly does it approach 0? So we're going to say that it's sinusoidal. Sinusoidal primarily so that we can use phasor analysis, which is going to make our lives a ton easier. We know that it's going to decay to 0, but how far will it penetrate before it approaches 0? And what happens to the magnetic field? What does it actually look like inside of the conductor? Since this problem really only has one dimension of variability, which is the vertical or z dimension in this case, we're going to reduce the vector differential equation to a scalar one. Remember that the left-hand side used to involve a Laplacian operator. Well, since there's only a z dependence, we're going to now reduce that down to a single second derivative with respect to z. And the right-hand side, of course, is going to remain unchanged, but it's now going to just be b sub x. I guess it would be fine if you wanted to write of z over here. So, since the magnetic field is sinusoidal, anytime that you have a sinusoidal excitation of a system, you can apply phasor methods. And the most important, the most valuable thing that we get from phasors is the ability to replace time derivatives. Notice that that's a time derivative right there. We can replace that with j omega b sub x of z. Now, if you're not an electrical or computer engineer, this j is probably troubling to you. Just remember that's the square root of -1, which other people call I, but we have another use for I, so we use j instead. So we have here a differential equation where the left-hand side is a second spatial derivative and the right-hand side is just now a constant. So this right here is a constant multiplied by the function b sub x of z. I'm going to replace this constant with gamma squared. That's the only change I'm making in between those two steps, is that gamma squared is equal to sigma mu sub 0 times j omega. And this equation, 17.26, has a well-known form of its solution. If it's spatial second derivative on the left and a constant times the function on the right, we end up with an exponentially decaying function as the solution. So equation 17.27 is the well-known solution to equation 17.26. But remember that we had gamma squared is replacing sigma times mu sub 0 times j times omega. And so I've represented those right here. So we know that the right-hand side of this equation is imaginary. It's imaginary because of the j. And if you take the square root of j, the question is, what is that equal to? Because we know that the square root of -1 is equal to j, but what is the square root of -1? Well, as it turns out, it's going to end up with a real part alpha and an imaginary part beta. And as it turns out in this case, alpha and beta have the same value, and that value is omega times mu sub 0 times sigma divided by 2. So if we know omega, which is the excitation frequency, we obviously know mu sub 0, that's a global constant, and if we know the conductivity of the material, we can use those to find alpha and beta. And then the solution, let me just scroll back up here to equation 17.27. Remember that this solution says that it's e to the minus gamma z. But gamma, right here, has both a real part and an imaginary part. And we know that if you have an e to the j something, that's like an oscillation. So this is going to be an oscillation. That means how rapidly is it sinusoidally oscillating. But e to the minus real part, that's going to be a decay. So the real part alpha controls how quickly does it decay, and the imaginary part beta controls how quickly does it oscillate while it's decaying. You know, eventually it's going to go to 0, but while it's going to 0, it's going to flip back and forth a few times. But in this one example, alpha and beta are equal to each other. That will not always be the case, that alpha and beta are equal to each other. But we know that in this case, we're going to have a solution which is an exponentially decaying sinusoid. And so we have b sub 0, whatever the constant is right at the top, and there's an exponentially decaying term with an e to the minus alpha z, and there's a cosine or a sinusoid term, cosine of b times t. So we understand e to the minus alpha z. We're familiar with things like this all the time. We're familiar from this from studying capacitors decaying, for example. We understand that there's a constant. There's a dissipation constant here, and so we know that it will have dissipated to or decayed to 37% its initial strength. You know, we often refer to it as a time constant. In this case, it's not decaying in time; it's decaying in space. So it will have decayed to 37% of its original strength by the time it reaches 1 over, that should have said alpha, 1 over alpha, which is referred to as the skin depth. So, you know, you can have, let me scroll back up here. Instead of e to the minus alpha times z, we could have said e to the minus z divided by the skin depth. And so the skin, I drew that backwards. So that's going to be the skin depth there. So the skin depth is sort of like a time constant. It says how far do you have to go into the material before it has decayed to 37% of its original value. Let's see this with some real numbers. Sketch the wave that results from a magnetic field 10 cosine of 10 to the 6th t. So that's a 10 megahertz wave is applied to the surface of a solid piece of copper, which has conductivity of 6 times 10 to the 7th Siemens per meter. What is the skin depth for this wave in copper? How far does it penetrate into the copper? Well, we know that alpha is equal to beta, which is equal to the square root of omega times mu sub 0 times sigma over 2, which is equal to the square root of 10 to the 6th times 1.2566 times 10 to the negative 6. That mu sub 0 pops up all the time, so that's the constant that we already knew, times 6 times 10 to the 7th, that's our conductivity, all of that divided by 2. And so when we do that calculation, we find that it is equal to 6.14 times 10 to the 3rd. And the skin depth then is 1 over alpha, which is 1 over 6.14 times 10 to the 3rd, which it turns out to be 1.63 times 10 to the minus 4th meters, which is about 0.16 millimeters. So it's about 1/10 to 1/5 of a millimeter, maybe about 1/6 of a millimeter. Think about how thick a millimeter is. That's about the thickness of a dime. We're talking about 1/6 of the thickness of a dime. And then what does the function look like? B sub x of z is equal to the initial strength, which was 10, e to the minus 6.14 times 10 to the 3rd z, times the cosine of 6.14 times 10 to the 3rd times t. So if we have the wave coming in, so it's subject to the, oh, that's horrible. So it is subject to the surface, and when it hits the surface now, it's going to start to decay. And how quickly does it decay? It decays over the course of about 0.16 millimeters. And it depends on how far do you want it to decay. Here I've decayed down to about 1/3 of its initial value. If you wanted to get down to 1/10 of its initial value, you'd have to go just a little bit deeper, but you get the picture of about the range over which it's decaying. Here's a really interesting example that has a very practical application. We have a microwave oven sending waves into a sphere of water. So I'm imagining that somehow I've got a sphere of water sitting in the middle of my microwave oven, and here's the frequency of a microwave oven, and here is the conductivity of tap water, about 30 millisiemens per meter. Notice how much lower that is as compared to, here we have 60 million siemens per meter, and down here we have 30/1000ths of a Siemens per meter. So conductivity of tap water is much, much, much less than that of copper, but nonetheless it is still a conductor, and so we can study the strength here. So at what depth will the wave strength have decayed by 50%? Well, the first thing we're going to need to do is we're going to need to calculate omega. We're given F, so 2 pi times F, so 2 pi radians per revolution, and revolutions per second is the F. This is going to give me 1.54 times 10 to the 10th radians per second. And then alpha is the square root of omega mu sub 0 sigma over 2, which is the square root of 1.54 times 10 to the 10th times 1.256 times 10 to the minus 6th times the conductivity, which is 30 times 10 to the minus 3rd. All of this divided by 2. Take the square root, and we end up with 17.0. And if we want to know at what depth will the wave strength have decayed by 50%? So I'm going to see what is the magnitude of b sub x. So I'm omitting the sinusoidal part. I'm just looking at what is the exponential decay part. B sub x divided by its initial value is equal to e to the minus 17, not t, z. E to the minus 17z. And if that's equal to 0.5, then I can take the natural log of both sides. So this is going to give me negative 17z is equal to the natural log of 0.5, and that gives me that z is equal to the natural log of 0.5 divided by negative 17, which is 4.1 centimeters. And I told you that this had a practical application because it explains that if you put something that is composed of water, and like much of our food is composed of water, just like much of our body is composed of water. So you can model a piece of food by just putting water in there, that the magnetic field, the electromagnetic wave, will have decayed to 50% of its original value 4.1 centimeters in. So that's like 1.5 inches. And if you go further in, of course, it will decay even further. It will decay pretty rapidly. This explains why you can't cook a turkey in a microwave oven, because you would burn the surface of the turkey and the inside of the turkey would remain completely uncooked. That the microwave oven is relying on the penetration of the waves into the material. It also explains that if you're heating up a big dish of food, you should scoop a little bit out of the middle so that the magnetic fields can get in on all sides of it. This to me, this is, in the course of 5 or 10 minutes, we've gone from these highly theoretical representations of Maxwell's equations to something very practical that impacts our lives. And yes, it's not the profound impact. The profound impact will come next time. But I love that we can get so quickly from Maxwell's equations to a practical application. So what have we seen? We've just seen everything today. The continuity equation, derived from conservation of mass. We talked about displacement current, that it behaves very much like regular or conduction current in that it can create magnetic fields. We have the final form of Amperes' law in both its point form and its integral form. And then it joins its peers as part of Maxwell's equations in point form and integral form. We have the constitutive equations, and we have the Lorentz equation to describe the force. And then when applied to conductors, Maxwell's equations can be used to model the exponential decay of a sinusoidal magnetic field applied to the surface.